Hi ladies and gentlemen. In the last class we have understood a 4-bit parallel adder. That is, we start with a full adder, then we make 4 instances of the full adder, and then we put them in parallel and make something called a 4-bit parallel adder that we use for binary addition, 4-bit binary addition. Now we are in this video we understand a 1-digit BCD adder using this 4-bit adder. So let me start with that presentation. So the speech is organized into your learning outcomes, the design of 1-digit BCD adder, then the design of the correction circuit to make an invalid BCD valid, then the BCD adder in Verilog, how to implement BCD adder in Verilog, then the BCD adder with 7483 ICs, and finally the summary of what you learned. So what you will learn in this video is that you will learn to realize a 1-digit BCD adder using 4-bit adders. Then you will design a circuit to detect the invalid BCDs. Then you will implement the 1-digit BCD adder in Qux and Verilog. Then you will appreciate the wiring diagram of the BCD adder using IC7483. So BCD representations for decimals from 0 to 9 are the 4-bit representations. Like all values from 0 to 9, say the binary patterns from 000 to 1001 is equivalent to their BCDs. But the remaining patterns from 10 after 9 there are no BCDs. So the patterns from 1010, that is 10 to 111115, they are invalid patterns. There cannot be such BCDs. So what is a BCD corresponding to the decimal 10? The decimal 10 corresponding to the BCD value corresponding to decimal 10 is 0001 0001, that is 0001 corresponding to this 1, and 0000 corresponding to this 0. How do I obtain this? What I get is 1010. This is a binary pattern. How do I get 0001 out of this 1010? That is by adding 6 to this. If I add a 6 or 0110 to 1010, it becomes a value 0001 So the point is that how do I make an invalid BCD valid? That is by adding 6 to the value. If it is 1010, you add 0110 to that, it becomes 10000. If it is 1111, you add 6 to that. So that way you make an invalid BCD valid. So the BCD addition is usually done by a 4-bit binary adder. Suppose if I want to add BCDs 2 and 3, 2 is 0010 and 3 is 0011. So what you get is 0101, that is equivalent to the BCD equivalent to 5. But the problem comes when this sum exceeds 9. See, if it becomes a pattern between 1010 and 1111. Or if there is a carry generated, then the BC then your sum value becomes an invalid BCD. That is, I use a 4-bit adder to which I apply 2 BCDs, valid BCDs indeed, and the sum can become invalid. When does a sum become invalid? When the sum exceeds 9, that is when the sum is a pattern between 1010 and 1111. Or if a carry results due to summation, if a carry results, then the resulting sum becomes an invalid BCD. So how do I make that valid? That is by adding 6 to that. So if one of the conditions is met, like if the carry in the first addition is 1, or the sum pattern is a pattern between 1010 and 1111, then I have to add a 6 to the sum, okay, to make the BCD valid. Now I have to design a correction circuit to add 0110 to the invalid BCD sum. If the invalid BCD comes, then I should be able to detect that. Then I should be able to correct that. How do I correct that? I add a 6 to that. So I have to design a circuit for that. So the output of such a circuit should be logic high if either the carry output of the first stage is high, that is the carry, if there is the first summation results in a carry, or the sum output of the first stage that falls in the range 1010 and 1111 inclusive. So let us analyze this case by case. Let us see the conditions. Let us see the cases where this S3, S2, S1, S0 falls within 1010 and 1111. So in that case, for all patterns of sum S3, S2, S1, S0 from 1010 to 1111, the output of that circuit, whatever correction circuit I am designing, that should be a 1. So I can put this in a truth table. I'm sorry, I can put this in a Karnoff map, a 4-variable Karnoff map, and I can design a circuit for this. So such a truth table will look like this. Here it is the patterns up to 1001, that is for all patterns from 0000 to 1001, output Y is a 1. For the remaining patterns from 1010 to 1111, the output is a high. So that I can enter into a Karnoff map like this: S3, S2, S1, S0. I say 0000, then 0011, 1111. These are the last 6 cases. These are the last 6 ones coming in this truth table, in this Karnoff map. So this results in two quads. There's one quad here. This is nothing but this. The term corresponds to this red oval, that is S3, S2, S3 and S2, because these are ones. This is an SOP expression, though this is S3, S2. And here, corresponding to this blue oval, I have this term S1. Here what does not vary is S1, S1, S3, that is S3, S1, S3, S2 or S3, S1. Okay, S3, S2 or S3, S1. Now there is one more condition. If the carry out is 1, again the correction logic should be high. So I can simply or C out to this. So if C out is 1 or S3, S2 or S3, S1 is 1, then Z, the correction circuit Z should be high. So I designed this correction logic in this way, that is Z equal to C out or S3, S2 or S3, S1. This came from that Karnoff map, and this came by my logic, that is if either C out is high or this is high, then my Z should be high. So Z is C out or S3, S2 or S3, S1. Now this variable Z can be configured to add a 0110. Whenever this Z becomes a high, 6 should be added to that. So I can configure this variable Z in such a manner that whenever Z is high, it adds a 0110 to the second adder. So that adder looks like this. My BCD adder looks like this. See, this is my first adder block. This may be a 7483 or any 4-bit parallel adder. This is a 7483 adder or any parallel adder. Here I have the inputs A3, A2, A1, A0 and B3, B2, B1, B0, and the input to C in. I keep it at logic 0. Here I can apply one BCD. I should apply a valid BCD here. I apply one BCD here, the other BCD here. So you get the sum S3, S2, S1, S0. This is my sum. If these numbers are, if this value is below 9, there is no problem. But if this value is above 9, or if this C out is a 1, then this logic I designed, that is, what is that? That is S3, S2. This is my S3, S3, S2, or S3, S1, or C3, C out. If any of these conditions are met, then the output Z is a 1. Either if this S3, S2, S1 is S0 falls between 10 and 15, or the C out is a 1, then Z becomes a 1. Now if this Z equal to 1, now this sum is given to a second 4-bit binary adder. The sum S3, S2, S1, S0 is given to another 4-bit adder, okay, to which I give another input, that is here this B3, B2, B1, B0 is connected to S3, S2, S1, S0 respectively. and this A3, A2, A1, A0 is configured with Z. Here I see that this A3 and A0 I permanently keep it at logic 0, and this A2, A1 that is connected to this Z output. So that when Z equal to 1, this A3, A2, A1, A0 is 0, 1, 1, 0, that is 6. Okay. So whenever this Z is high, I add 6 to this S3, S2, S1, S0. Okay. Why? Because this Z is connected to A3 and A2. Whenever Z becomes a high, the what gets applied here is 0, 1, 1, 0. What happens when I apply 0, 1, 1, 0? Because 0, 1, 1, 0, because this whatever invalid BCD coming here, that becomes a valid one. What if this BCD is valid? Then this Z equal to 0. In that case, I am applying this A3, A2, A1, A0 is just 0, 0, 0, 0. So nothing is added to my S3, S2, S1, S0, and the same thing happens. Now this carry, this Z acts as a carry also, carry output also. Whenever this invalid BCD pattern comes, the carry becomes a 1, or else the carry is a 0. So this carry together with this Z or carry out together with S3, S2, S1, S0 becomes my BCD sum. So this is how I design a one-digit BCD adder. So the crucial thing is the design of this correction circuit. Once you understand this logic and how I use this Z to make a 0, 1, 1, 0. Once you understand that, it is very clear. Now I can simulate this thing in cubes. I will show you that simulation. I open this project, binary adder project. So many files are there in binary adder project. Now I will go here, this and now you can see that this is the circuit for a binary BCD adder. So here this is my first adder block. This adder block, if you see, I will go into the sub circuit and you can see that it's my good old full adder block. This is my good old 4-bit adder. So there are 4 parallel adders, 4 full adders here. This is a 4-bit parallel adder. So I have 2 instances of such a 4-bit parallel adder here and here. Okay. Now what happens is I apply my BCDs here, I apply A3, A2, A1, A0. Of course, they should be valid. A3, A2, A1, A0. This is my first BCD. This is my BCD B3, B2, B1, B0. Okay. So these are my sums, and this is my carry. This pin is my carry. These are my sums S3, S2, S1, S0. Okay. Here I designed this correction logic. This is my S3, S2, or this is my S3, S1. Okay, that is ORed with my C out or C3. Okay. So this S3, S2, S1, S0 is applied to the second full adder. So sorry, second 4-bit adder. Second 4-bit adder, and this Z, this value, this is used to apply a 0, 1, 1, 0. You can see that this point is always held at a 0, logic 0, and this point is also held at logic 0, but these two are at Z, so that when Z becomes a 1, it becomes 0, 1, 1, 0. When Z becomes a 0, it is adding 0, 0, 0, 0, and it is adding nothing to that. Now you can take out this S3, S4. This is my Z out, which I mark as S4 for the sake of convenience. S4, and this is S3, S2, S1, S0, the 4 sums. Now this is just the implementation of the circuit we saw in the presentation. Now I can simulate this circuit. Now I get this thing. Now I have given arbitrary signal, so some of the input BCDs may not be valid, so I don't consider those cases where I apply invalid BCDs. I consider only the case of valid BCDs that are applied, because I used signal generators of arbitrary configuration. So some of the patterns coming at the input may be invalid, so I don't consider that. But if you come here, you can see that 0011, it's a valid pattern. The next is a 0 0 0 0. So the result is a 0 0 0 1 1. That is a 0 3. Okay. Now if I come here, this is 8. Any other? Here it is a 0 0 1 0 0 0 1 0. That is 2 plus 2. 4 should be coming. So it is 0 0 1 0 0. It is 0 4. Okay. Or if you come here, it's a 1000. Okay, 1008. This is 0010. So I should be getting 10. 10, I should not get it as 1010. Instead I should get it as 1. That is the first BCD, that is 0001, then 0000. It is of the form 10. Or if you come here, this is 1000 plus 100, that is 8 plus 8, it should be 16. So I should be getting 0001, 0110. That is what I am getting. Here it is 1. 1 is nothing but 0001. This is 0110. It is 1 6. Okay. Here if you say it is 1001 is a 9. This is 100. Both are valid BCDs. Or 9 plus 8 becomes a 17. So what I am getting is a 17. It is 10111. It is 0001 0111 17. Okay. So this is how I demonstrated the operation of one-digit BCD adder using cubes. So let me go back to my presentation. Now, how do I implement this BCD adder in Verilog? It is not 4-bit adder; it is a BCD adder in Verilog. I will show you this in a editor better. So here, this editor shows the BCD adder. So in this BCD adder, the basic unit is a 4-bit adder. So I grave include 4-bit adder. Grave include 4-bit adder. Now what I do is I start a module BCD adder n module. Okay. Then it has a sum output. That's a 4-bit pattern. That's 3 to 0. That's a 4-bit pattern. Sum is a 4-bit pattern BCD sum. That is then output wire. There's a carry output. That is a wire. And there are two inputs are there, X, Y, that are 4-bit. And there is an input wire C in, 1 bit C in, that is a carry in. Then there are some intermediate values, like I have a wire 03, sum 1. What is this sum 1? This is the sum of the sum bits of the first 4-bit adder. Okay. And then this is the pattern 0110 I have to make. Okay, so these are a 4-bit thing. This is sum 1. This is the output of the first BCD adder. It goes to the input of the second first 4-bit adder. The sum 1 is the sum of the first 4-bit adder, and this goes to the input of the second 4-bit adder. And X I am using to generate my pattern 0110. Okay. Now I have some internal nets C0, C1, A, B, C, D, etc. That will be very clear to you when I describe these things. Now first I make an instance of the full adder, 4-bit adder. That's a 4-bit adder. Say add 1, some name add 1. What is it generating? It is what is it applied? What input is applied? X and Y are applied. That this input X and Y are applied here. Okay, and it generates a carry C0 and a sum 1. Okay, sum 1. That's a 4-bit sum 1. Okay. Now what I do is I have to generate the correction circuit. So correction circuit is actually S3, S2. S3 and S2, or S3 and S1, or C3. Okay, so how do I do that? I make an AND gate, a 2-input AND gate with output say A. I put it as an internal net. Sum 1 3, so it is ANDing sum 1 3rd bit and sum 1 2nd bit, S3 and S2. Okay, and the output is given in the as the internal net A. And the second AND gate, it is some 3, someone 3 and someone 1. Okay, that is S3 and S1. That is given to the net, that is stored in the local internal net B. Okay, now I have to over this A and B to form C. A and A over B, that is equal to C. Now there is one more condition. Now I have put the condition on S3 S2 and S3 S1 or S3 S1. Now I have to add C0 also. If C0 is 1, then only it becomes invalid. So what I do is C or C0, that is C out, because this is my, in the figure in the diagram I showed it as Z. Z is actually the carry out, so I mark it as C out. What is that C out? That is the output of my circuit, C out. The C out is C or C0, C or C0. Now I have to add 0 1 1 0 whenever either when the C out is 1, or if this what should I say, if this is 1, the C out is 1, then what I have to do is I have to add 0 1 1 0 to the circuit. So I earlier we use, remember this diagram here, I connect this logic circuit output Z to this way, Z to make 0 1 1 0. So how do I do here? It's very easy. I assign a x. I kept this variable x here. It's a 4-bit variable. So that assign x2 and x1. That is second bit and the first one. That is 0 1 1 0. Okay. The middle 2 bits I make it C out. Assign x2 equal to C out. Assign x1 equal to C out. The other 2 bits I make it 0. That is x3 and x0. So capital X is nothing but 0 C out 0. When C out is 1, it becomes a 0 1 1 0. When C out equal to 0, it becomes a 0 0 0 0. All I have to do is to add this x to my sum 1. For that I use the next 4-bit adder. I use another instance of my 4-bit adder that I call as add to 4-bit adder add to. What is this? I add sum 1 with x. X will be 0 1 1 0 when C out is 1. This C out is 1, or it is 0 0 0 0. So whenever the invalid BCD comes, 0 1 1 0 is added to sum 1. Otherwise nothing is added. So what is it generating? It generates a sum, that is my output sum. Okay, and some carry. I am not interested in this carry. Okay, that I put as a local, as an internal net. I am not interested in that. I am interested in this C out only. That is the output of my logic circuit. So what I get is sum, and if I look at the C out and sum, I can know my that is my output sum result. Now I can, for testing this, I can make a test bench. Test bench is similar to my 4-bit adder test bench. What I do is I include grave include BCD adder.p. This is the unit under test, and I start some module test bench. These registers x, y, these are for input values, and this register is for the carry in. Okay, so the sum is a wire, that is the output sum, and the output C out, that is a wire. Now I make an instance of the module BCD adder, that is BCD adder, say some name y1. What is it? What are the inputs going into this? X, Y and C in. X, Y and C in. What is the output of that? Sum and carry out. Okay, sum and carry out. Now what happens? See, then I use a monitor as usual. I use a monitor here. Okay. So this carry out and sum I have to see. So here I dump into some file. I will give it a, what should I say, BCD adder .bcd. So here I give some valid patterns. Here I give valid pattern 0 0 0 0 0 0 0 0 valid pattern 1 0 0 0 0 0 0 0 1 0 0 1 0 0 1 1 0 0 0 1. Yeah, I will do something else similar. I'll make it as 0 1. Okay, then I have a 0 1 1 1 plus 0 1 0 1 0 0 0 1 0 0 1 0 0, that way. So now I can run this thing here. First I have to I say I verilog dot v. Now that runs without any problem. Now I do I verilog BCD adder TB. Okay, test bench I am running with a out as the executable file. So that is created. So I run a dot out. Okay. Now you can see that initially these are indeterminate state. Here it is I am adding the BCD 0 with the 0. So the sum is 0 and the carry is 0. Okay. So the number is 0, 0, 0, 0. Okay. And here 1, 0, 0 is added with 0, 0. What I get is 1, 0, 0. Carry out is 1. Here I add 8 with 9. So it should be 17. 17 means the carry out is 1. So this is 0, 0, 0, 1. This is 7, 0, 1, 1, 1. Okay, I am adding 8 with 9, so I should be getting 17. I am getting 17. The carry input, this comes here. The 0, 0, 0, 1, that is a 1, 0, 1, 1, 1, that is a 7. Now I am adding 1, 0, 0 with 0, 1, 0, 1, that is a 8 plus 5, that should be a 13. Okay, 13 is this is 13 because it is 1, that is a 0, 0, 0, 1, 0, 0, 1, 1. This is 1, this is 3, 13. And here it is 7 plus 5, that's a 12. So it should be 0, 0, 0, 1. This is 0, 0, 0, 1, 0, 0, 1, 0, 1, 2, 12. And here it is I am adding 1 with 4. It becomes a trivial thing. 5 with the carry 0. That's simply a 5. So this is how I develop a one-digit BCD adder in Verilog. You can go to the lab and take the 7483 chip, and you can realize a BCD adder with that. This diagram may not be that clear to you from the first observation, but you can use this diagram to wire up your circuit. So this is where this is the first 7483. This is a 4-bit adder or parallel adder, 4-bit parallel adder, to which I apply the BCDs A3, A2, A1, A0, and B3, B2, B1, B0. Okay, B3, B2, B1, B0. Yeah, here it is B3, B0, that way. You can apply to sets of inputs. Okay, then you can keep the this carry in a logic 0, ground should be there, supply everything should be there. Now this sum will be, some of the sum patterns will be invalid. So what I do is I use these two gates to realize a correction circuit, that is S3, S2 or S3, S1 or C3. I can use this circuit. So this output, this is the output of the OR gate. This is my thing Z. Okay, Z is used to apply a 0, 1, 1, 0 pattern here. Okay, so this is my second 4-bit adder. This is a second parallel adder to which I apply the sum, the sum of this stage and 0, 1, 1, 0 or 0, 0, 0, 0, depending on the logic, depending on the value coming here. So this creates here. Then I test my output. Then I test my outputs with by connecting normally on LEDs. Okay, this you can connect in your lab and verify. Apply valid BCD patterns here. Here A and B, you hear valid BCD patterns, and you observe C out S3, S2, S1, S0, and you can understand the operation of the BCD adder. Now coming to the end, what you learned in this video is that you learned to realize a BCD adder with the 4-bit adders. Then you implemented this in cubes and Verilog. Then you appreciated the wiring diagram of the BCD adder using IC 7483. And that is the end. I thank you all.